Hello students, welcome once again to my channel. Now in this section, this video contains a methodological content, and we want to talk about the MJO, which is basically the Madden-Julian oscillation. Now the Madden-Julian oscillation is an atmospheric phenomenon which most of the time affect the Australian weather system. It's one of the dominant features that actually drives the Australian weather system in the warmer months and the early months of the Australian weather system, somewhere March all the way to October, November. Now, just a brief history. The Madden-Julian oscillation was discovered by two scientists in the year 1971, and it was discovered by Roland Madden and Paul Julian of the NCAR, which is the American National Center for Atmospheric Research. Now, it affects mostly the Australian weather system. Now, the whole phenomenon starts basically the whole phenomenon starts from the Indian Ocean, specifically the Western Indian Ocean, and therefore it fades, dissipates, and also ends at the Pacific Ocean, which is the Eastern Pacific Ocean. Now, in this video, we want to cover some few things. So we want to look at the content of this video. Now, we want to look at what the MJO is. We'll also look at how the MJO occurs and its effects, and also we also look at the phases of the MJO and also the impact of the MJO on climate. Then also we'll look at why we should care about MJO. MJO. So we look at what the MJO is. Now, MJO is an eastward moving pulse of convective activities, um, enhanced cloud precipitation, and these move in association with the winds, and it recurs after 30 to 90 days in the tropical atmosphere. So these winds that are moving are already formed convection, already formed precipitation clouds, right? And it reoccurs after 30 to 90 days in the tropical atmosphere. So when we talk about the tropical atmosphere, we are referring to the region within the Tropic of Cancer and the Tropic of Capricorn. So basically the equatorial or the tropical regions, right? Now, it reoccurs after 30 to 90 days. Why? Because MJO is the largest element of the intraseasonal variability in the tropical atmosphere. Now, what does it mean? Now, when we talk about the intraseasonal variability, we are talking about the changes that actually takes place within the seasons. Now, within these seasons, now in a season we have the summer, the winter, the autumn, and the spring. Now each of these seasons takes place within a year, and it lasts for about 3 months, which is basically the 90 days. So when we are in the summer, season, we realize that we will have the summer season for about 3 months, which is 90 days before a new phase. Okay, so let's take for instance we have winter taking place for also 90 days, and also the autumn and also the spring respectively. So that is basically the intraseasonal element, and it reoccurs 30 to 90 days. Okay, so when we talk about the MJO basically starts from the Western Indian Ocean and also crosses the maritime continents, and it therefore dies, dissipates, and also fades in the Eastern Pacific Ocean, but then also with a speed of about 14 to 29 kilometers per hour, which is about 9 to 18 miles per hour. Now, depending on the speed, so let's take for instance, if the speed of the winds is about 14 kilometers per hour, or about 14 kilometers per hour, then we expect that it should take about 90 days before another phase of the season occur. But then if it is about if we have more of the wind speed, which is about 29 kilometers per hour, then we expect that it should take less than 90 days for a new phase to also take place. All right, so just more information about the MJO. Now, comparing the MJO to the nino oscillation, which is the ENSO, in our previous video we discussed about the ENSO, so I'll leave the video link in the description. Now, the ENSO, we established the fact that it is a standing event, unlike the MJO, which is a moving event. It is always propagating around the equator for about 30 to 90 days. But then the ENSO is a standing event. It's always stationary, not moving. But then the MJO is always propagating, moving, traveling around the equator, right, for about 30 to 90 days. Then also when it travels, it moves above the warm part of the Indian and also the Pacific Ocean. Then also it's more information about that. It is characterized by eastward spread of large regions of enhanced and also the suppressed tropical rainfall. Now we'll talk about the enhanced and also the suppressed rainfall or precipitation or convective activities phases that actually takes place, and this is mainly observed over the Indian and the Pacific Ocean. Now let's look at how the MJO works. So basically what happens in this case is that the enhanced tropical rainfall, is first found at the western Indian Ocean, which is basically where the whole thing is being formed, right? So it starts from that particular region. It is then also spread eastward into the warm waters of the tropical Pacific, and finally dies out as it moves on the cooler waters over the eastern Pacific. So it is more effective when it's moving on the warm waters. Then it fades and dies out when it's moving on the cooler waters, right? Then so as it move in this particular cycle, starting from the western Indian Ocean, then moving through the maritime continent, and also face or ends at the eastern Pacific. That's the first cycle. So when this cycle ends, then a new cycle also starts all the way from the western Indian Ocean again. So it's basically a cyclic process. Then also the a wet phase of enhanced conversion is followed by a dry phase, right? So on the wet phase, we should expect convective activities. We should expect enhanced convection. But then on a dry phase or on the cooler phase, we should expect the suppressed rainfall or suppressed precipitation. Then so each cycle lasts for approximately 30 to 90 days, and these the MJO also is made up of phases. We'll talk about the phases later in the video. Now when we talk about the MJO, we want to look at how the MJO is being formed, right? So basically over here we have the western Indian Ocean, then over here we have the eastern Pacific Ocean. Now what happens in this case is that we have ocean surfaces are very warm, right? So if ocean surfaces are very warm, we expect that convective activity should also take place over there. So since ocean surfaces are very warm due to insulation, right, therefore there is rising of water vapor, there is lifting of air masses. So as these air masses rises, there is adiabatic cooling where this air masses becomes very cool. Now it rises because of its less density. So there is adiabatic cooling takes place. Now when the adiabatic cooling takes place, it gets to a point where it reaches a point of saturation where the atmosphere has received some amount of moisture. Then at that particular point we have clouds being formed. Then if these clouds are formed, condensation of water vapor takes place, which brings about precipitation. So in this particular case, we have convective activities, rainfall being formed in this particular region. Now at the lower levels here we have low pressure systems, and above this convective phase we have what we call the high pressure systems in this particular phase. So since we are experiencing convective activities over here, we call this region the enhanced convective phase or the enhanced precipitation phase or region, right? Now because there is a high pressure system created above this enhanced convective phase, what will happen is that there will be divergence of air, right? A divergence of air basically means the falling of the air. So in this direction, so basically in the opposite direction, in this direction, also in that particular direction. But then if this subsidence occurs, there is a subsidence that actually occurs. So subsidence of air is basically the falling of air. So as the subsidence takes place, it leads to what we call the adiabatic heating. Now adiabatic heating decreases the amount of relative humidity. Now above this level we can see winds, right, air with air masses which are moving, but these air masses are moist. But then if this subsidence occur and adiabatic heating takes place, what does that? It reduces it increases the relative humidity, thereby taking moisture out of the system, and therefore the air mass, the characteristics of the air mass in that particular region becomes very dry and therefore falls to the ground. And this phase actually becomes the suppressed convective phase or the suppressed precipitation phase. So these three phases, so in this particular direction also we have the suppressed convective phase. At the mid level here we have the enhanced convective phase, and in this particular direction we have the suppressed convective phase. Now so these are in three phases. This phase here is what actually undergoes the eastward movement along the equator for 30 to 90 days. So what is before and after the convective, the enhanced convective or the enhanced precipitation phase is the suppressed convective phase, and what will be before and after the suppressed convection and or the suppressed precipitation phase is the enhanced precipitation phase. So these three phases are what actually recurs around the equator for 30 to 90 days. Now let's look at more detailed about this phenomenon. Now let's look at this video. Now in this video we have a dog over here. Now this dog is representing the Madden-Julian oscillation, or we are referring to this dog as the MJO. Now so I said it influenced the Australia weather system, especially in the warmer months of the Australia weather system, somewhere March to October, November, right? So this MJO, which is the MJO, recurs around the equator for about 30 to 90 days, and when it is moving they are made up of pulse of winds, clouds and precipitation which are moving around the equator for 30 to 90 days. Now in some cases as it moves around the equator, what happens that it carries waves of weather. So we have waves of weather in that region. So we have waves of weather in that particular region. It carries a lot of rain, precipitation and clouds, right, around these regions. So we can see rains, right, moving, and also it creates tropical cyclones. We can see tropical cyclones being created. Tropical cyclones are created on warmer ocean surfaces, which are warmer, and also in the low pressure center, right? So tropical cyclones are being created. So the MJO creates tropical cyclones. In some cases rains in the Australian weather system, which is affect mostly the northern part of the Australian weather system, and but then also it influences further north, further south in the Australia weather system, because it carries clouds, convective activities in that particular region. The MJO sometimes is unpredictable, because in some cases it can bring periods of in some cases we experience periods of rainfall where we have convective activities, but then also in some period we have no activities taking place, or just a little activities taking place, right? So we can see that in this video. So it is sometimes unpredictable, then moderate conditions, period of little activity, and also period of no activity. Now further we'll talk about how it also affects the Australian weather system. Now I said these are eastward moving winds and clouds, right, along the tropics, right, and they move along the tropics for about 30 to 90 days. Now if you look at the phases over here, in the mid levels here we have the enhanced convective phase. So you can see it it is carrying cloud precipitation. But then what is before the enhanced convective phase is the suppressed convective phase, or the suppressed precipitation phase. So this is what actually moves around the equator for about 30 to 90 days, right? But then it affects most of the time the northern part of the Australian weather system when the MJO is being settled at that particular place. But then also when it moves away from the northern part of the Australian weather system, we experience um, low we experience drought in that particular region. So the MJO influences the northern part of the Australian weather system, thereby bringing rainfall, precipitation, and floods. Right now, its relation to the monsoon trough. The monsoon trough is a belt of low pressure, and the monsoon trough is basically formed a thin line which is formed around the equator, right? But then also is a belt of low pressure where the northern and the southern hemisphere trade winds are meeting. It also bring rainfall. We can see rainfall activities also in that particular region. So you realize that belt of low pressure bringing rains, right? Clouds are formed, precipitation and stuff. But then also it becomes very much intense when it moves towards the northern part of the Australia weather system. So it brings a lot of rain, floods taking place. Also, during that time, the MJO is always, as I said, it is not a standing event. It is always propagating. It is always traveling and moving around the equator. But then when the phase settle around the belt of low pressure, especially in the northern part of the Australian weather system, we see more of the convective activity. So you can see that we have it influences the belt of low pressure, and we have more of convective activities in that particular region. But then it gets to a time that the MJO. So this break in monsoon was as a result of the monsoon trough, which is a belt of low pressure, moving away from the northern part of the Australian wind system. And when this happens, we have the break in the monsoon. Now, in the break in monsoon, so we can see that the MJO is also moving away. This happens when the belt of low pressure, it gets to a time that it grows weaker and therefore moves away from the northern part of the Australian weather system. But then we see about high pressure system being created at the northern part of the Australia weather system. When this happens, we only see drought conditions in that particular region. So we don't see rainfall in that particular region. But then in the other region, we see the rainfall over there. Now, also we've talked about tropical cyclones which are being formed, right? They are formed on a system of low pressures and warm ocean waters, right, or warm ocean surfaces. So we have tropical cyclones being formed. Now when it gets to the eastern Pacific, right, it gets to the eastern Pacific, what happens is that we see at the further south of the Australian weather system, we don't see convective activities in that particular region, and we see them rather getting to the eastern part of the Australian weather system. So we see a lot of rains, flowers around those areas, but we see drought in the Australia weather system. Okay, so you see further south, but then it gets to a time that it's also influenced further south where we see rain in that particular region, and this moves in phases. We have the convective phase, the suppressed phase also. So basically that is a video explaining the MJO and its effects. Now let's quickly look at the phases of the MJO. So when we talk about the phases of the MJO, now the first phase is the enhanced convection phase, which is being developed over the Western Indian Ocean. So we are talking about the starting point of the MJO. It is being developed over the Western Indian Ocean with a convective phase, right? Enhanced convective phase. Then with the second and also the third phase, we have this enhanced convective phase moving slowly to the east over Africa, and also moving through the Indian Ocean, also part of the Indian subcontinent. on the fourth and the fifth phase, we see the enhanced convection has reached the maritime continent, that is areas around Indonesia and the West Pacific, right? So it moves towards the across the maritime continent. Now, for the fifth, seventh, and the eighth phase, we see this enhanced convective phase moving eastward, further eastward, and also dissipating or dying out in the western Pacific, right? And when it dies out over there, what happens is that a next cycle of the MJO begins, right? So basically, those are the phases of the MJO. So we have a picture over here, a figure over here indicating how these phases are moving. So we realize that in these phases we have it is moving in phase 1, phase 2, all the way to phase 8. So you can see that this color here, right, we see these are the converted phase, these are the suppressed phases. Now it has some kind of effect over the jet streams over here. So we realize that when we are moving over the cold phase, right, which is the suppressed phase, the jet streams grow in dimension, the speed increases, right? But then in the enhanced convective phase, the jet streams um reduces, which means that the speed reduces, right? And also it has its effects over the long wave radiation. We are going to discuss that one later in the video. So let's quickly discuss how does the MJO affect weather around the world. Now, in the formation, we realize that the MJO creates favorable conditions for tropical cyclones to be formed. Now, what are these favorable conditions? Now, these conditions include warm ocean surfaces, right, which we saw at the Indian Ocean, the Western Indian Ocean, moving over the maritime continent. These surfaces are very warm due to insulation. So these conditions are there. A belt of low pressure being created, or a center of low pressure being created, is one of the conditions needed for tropical cyclones to be formed. So it forms tropical cyclones around our weather systems. Then also we can see at the enhanced convective phase, it can bring the onset of monsoon seasons around the globe. So what it means is that depending on the phase that we are experiencing, the Australian weather system is experiencing, it can either delay or influence monsoon. So if we are having the enhanced convective phase, you realize that we have it influences rain, convective activity takes place, but then at the suppressed convective phase, it can delay monsoon formations, or the monsoon kind of activities taking place, right? So we have that one. Then also there has been evidence that the MJO influences the ENSO, which is the nino oscillation, and also it does not actually cause the El Nino and La Nina, but then it contributes to the speed and also the speed development, the speed of development, also the intensity of El Nino or La Nina episode, right? So that's basically the effect around the globe, or around the world. Now, why should we care about MJO events? Now, we should care about MJO events. Why? Because we have MJO creates some kind of effect on the monsoon, so it can modulate, right, control the timing and also the strength of the monsoon. Thereby it can delay or influences the onset of monsoon, which we've already talked about. Then also it influences tropical cyclones, which means that it can increase the strength of the tropical cyclones being formed. And also the most important thing we want to talk about here is that it results in the jet stream changes, right? It bring like altering the jet streams, which can bring cold air outbreaks and also extreme heat events. Now, when we talk about the jet stream is one of the important phenomenon that takes place in the upper troposphere. So it plays an important role in the extratropic region and also the temperate regions. Now, the jet streams are made up of meandering type of winds, right, which are moving in the upper troposphere. So these are taking place in the upper troposphere. But then also when these are moving, they move since they are meandering kind of winds, they move in the trough and the crest kind of movement, right, in those areas. When they move in the trough and the crest kind of movement, you can see that we have regions of high pressure and regions of low pressure in this particular wind, because these winds are kind of they move like a meandering kind of winds. So what happens is that there is an ascendance, right, which will create variations or anomalies in the pressure system. So you can see that we have the crest and the trough kind of wind. At the trough, we are experiencing pressures there to be low, and also at the that's at the trough, but at the crest the pressures there are very high, so it creates a variation, right, kind of anomalies in the pressure system, which would affect so it's going to affect the movement of the wind, right, or altering the jet streams and also the movement of the wind. Now when this happens, it will bring cold air, right. It's going to carry cold air mass or cold air from the pole. So it brings cold air from the pole towards the equator or towards the southern part, right. Then also it will also carry the warm air from the equator all the way to the polar regions or the temperate regions. So it kind of bring an exchange between the cold air or the cold air mass and the warm air masses in these various regions. So that's basically the jet stream. So even with that, through the exchange of the cold air mass and the warm air mass, it can bring cold air outbursts and also extreme heat events in that particular region. Now if you look at this diagram over here, you realize that when we have the suppressed phase, what happens that the jet streams speed increases, and therefore we have for the outgoing long wave radiation over here, when the jet stream speed increases